And this would be about binary parsing in C++ 23 style. So maybe let's start with something about me. I'm Hari. I'm working in Ambition. We are a subsidiary of Mercedes, and we develop all the fancy infotainment software for all the Mercedes car lines. And in my team, I'm working along with my teammates to establish connections between the other ECUs, and then we make sure that the underlying communication protocols are abstracted away, and then they get a stable API across multiple car lines. Yeah, and that's where I'm causing my damage now. And those are my social media accounts, and you can reach out to me. I have been working mostly in embedded systems so far. A little disclaimer. So I'm not an expert. I'm just a dude. I've been writing C++ for now like around 6 years. So take anything with a pinch of salt. And the views presented here are not of my employer. So I'm not representing my company. The project is done on my free time, so I'm not. The views are not of my company. But I did consider all the pains in the past from my other peers who work with me now and in the past. And we will walk through only a little smaller fragment of the original project, because the real project is now close to around 5,000 lines, and it would be really, really impractical to go through it in the talk now. And also, I also minimized the project here to be presented because most metaprogramming talks are like magic. So we can skim through basic version as much as possible, and this would make things better. And that way, we avoid this famous meme where you go to a class to learn how to draw an owl, and then they start with 2 circles, and then in the next slide, you end with an owl. And that's not how people want to have it. So how this came to be? So parsing binary data is like anything. It's like something every developer would come across in their life, right? When I started my career at Bosch, I used to parse all the CAN data, and then in my pet projects, I have to pass some image data like GIF files and maybe some audio files. Everything is binary. And then I didn't find any declarative way to do this. It was always like you have to write some sort of an IDL and then run a code generator to generate your all the parser code. It was a bit messed up for me. And then I thought, okay, maybe this is one of the things I can do with metaprogramming. And maybe around 2 years ago, I met Hannah Dusik over here in Meeting C++, and I proposed this idea to her, and she said, yeah, it looks like a good idea. Maybe try something, and then we can discuss next year. And then I had a small prototype, went back to her last year, and then she said, hey, it looks good enough. You can maybe present this year. And then and hence the project. So I have to thank 2 people for this. One is Hannah, and another is Chris Jusiak. Most of their works have inspired me to do this. So a special thanks to them. And as a side note, go to conferences, talk to people there. You would always learn something out. Yeah. So a fact check, or maybe a quiz. I don't know. Let's try. So what do you think would be the output of this program? So we have some function which reads a binary file, and then prints each of the members in it. In the struct. We just do a reinterpret cast of the complete struct and then read it from the file. We print individual members. And let's assume the file below is the file we provide to the program. So in this case, no tricks. It's quite straightforward in this case, at least. So it would work well because the structs is well aligned and so on. So it's nothing is a problem here. But then you get this. Someone wants a struct you want to read, but then you have one member whose size is just 1 byte. And then you assume and now we have a file which also kind of aligns with this. But do you think this would work?
No, it will be messed up because of the padding in the struct.
Exactly. So now the compiler would add 3 bytes in between because it's much, say it's faster to read, for example, and then it wouldn't no longer work because now the second 4 bytes are now considered as the second member of the struct, and then it gets misaligned. And then we also read some junk bytes from the end.
Yeah, and then it all depends on the word size of the processor too.
Yes, if you have a 64-bit processor, you have a 32-bit processor, maybe you are working on an 8-bit, or who knows, whatever. So now, okay, let's go back. We have the original struct, but now the binary format of the data itself says I have only 3 bytes for member 2. Maybe you have your own serialization format, and then the second member has only 3 bytes. But C++ doesn't have a 3-byte data member, so you should still use a 4-byte member. And now you do a reinterpret class. It still wouldn't work, right? Yeah, some undefined stuffs. So what is a right way to do this? So what is the solution? So you'll have to write, unfortunately, you'll have to roll out individually the reads, right? And this is similar to your memcopy, and then you'll have to make sure the sizes which you're reading are like exactly what you want to read. This works. Yeah, but let's make it better for readability. So I wrote, like, we have some context variables for all our member sizes, and then we read all the members. Cool, works. But then someone comes and throws a corrupted file. Maybe it was truncated, who knows? Or some network packet comes up, and then the packet was broken. It has only 8 bytes, but we need 12 bytes for our parser to work. We'll now have to handle file buffer exhaustion. So the new kid in the town is the std expected. So I thought, okay, let's use std expected, write a small error handling now, right? And it's not the cleanest code, it's a slideware, so it's not the cleanest code, I know. You can write it much cleaner, but yeah. I say, okay, if something goes wrong, I say that I return an error. So std expected is a box, right? The box either has a value or an error. So you open and you see if it has a value or an error. So this also looks well for me, at least for now. But someone else comes up and I say, I want one more struct to be parsed. This time I have a second member, which is a Boolean, and then the third member depends on the second member. Only if the second member is true, I would parse the third one. Yeah, okay. Then I copy paste the code, and then I say I had one more condition. I mean, you know the story. I mean, then you'll have few other structs coming up, and it has a nested structure or whatever. So nested structs. You might have a length prefix vector. You say my length is coming sometime at byte 4, and then my vector comes some elsewhere, but the length depends on the length is derived from the first member. Or you have a tag length and value, like a union, like a variance, where you say, okay, if my second member is equal to 2, then the upcoming member would be an integer, and it has a length of 3, else it is a string whose length is 6, all the variances. You might have to handle endianness, because binary formats can have endianness, so you might have to include a way to somehow represent both little or big endians. And to make things worse, I have come across files where you have a hint of the endianness, which says, okay, my file has this endianness, and then in runtime, you'll have to switch your parser. You might have to validate your values. Maybe you're getting some value from the network, and then say, okay, this particular member has to be between value A and B. Or I have to stop parsing right away. Delimited fields. For example, in a GIF file, you will have a set of records, like an array of records until the end of stream, and you'll have to go there until you meet the end of stream. So it's like a delimited fields, right? Or you have magic numbers. For example, again, GIF files have at the top a magic GIF string at the front. So or if you're a Marvel fan, then like Dr. Stephen Strange said, things got out of hands, right? You have too many things to worry about. So what are the possible solutions we have? So there are DSLs, like domain-specific languages, like Kaitai. I came across Kaitai first, and then then maybe your company says, no, we have licensing issues, so you can't use Kaitai, or you can't use any other DSLs. We might have to write our own. So then you write some custom DSL, and then you'll have to write a Python parser, which would parse the DSL and then generate the code for you. And then, this is, it scales well to a large extent, but then when you have variances in the project, for example, and then there are too many teams working, and then if the data is kind of being shuffled across them, it doesn't scale well anymore. The third one is the template metaprogramming magic. That's what I did. I'm sorry about it, but Yeah. And then the little surprise at the end. Yeah. And we'll come back to the surprise at the end. So I chose TMP. Why? Because at that time I wanted to explore the depths of the language, like how much I can learn and what can I do about the time. But more importantly, it's towards the end when the project became a bit mature, it was more about the surprise I was talking about, right? And we'll come to that at the very end of the talk. So what is a promise I'm giving to you? So we'll have a parser generator at compile time, which has no macros, has reasonably good error messages. Yeah, at runtime, yes, it's very easy to provide reasonably good error messages, but if you've been developing C++ for quite a long time, or even a very short time, you might know how horrible our compile errors are. But I'll say reasonably good error messages with the latest standards. And the parser is generated at the compile time, right? And there's a little link to the code vault. And const expr as much as possible. Why? It's the trend now, const expr as much as possible. So everybody, let's make it const expr. But now I would like to draw a small line here. By what I mean by generating the parser and the const expr compile time parsing are completely different, right? They are not the same. The main idea, the sole idea of the project is to generate the parser itself at the compile time. But you can still also in the compile time also parse the data, but that's not the sole idea. The main idea is to generate the parser, right? And then all the support, whatever Stephen Strange wanted. And we can also have validation of the fields. And for now, I don't support runtime NDNS handling. It was a bit difficult for me at this point of time, but maybe in the future, it also handles runtime NDNS. For now, it's compile time NDNS. And it works with any kind of stream. Like you can pass in any of your own custom streams. It works with span streams. It works with file streams and everything. So if you go to GitHub and then clone my project, what do you have to write? Unfortunately, you have to write something like this. So we'll have to have a descriptor, like how your structure looks like. And then you have to just call struct cast, similar to like static cast or reinterpret cast, which means like you are casting your stream to this particular struct, right? And then you have square bracket operators. Like the only problem we have here is this is not a regular struct, right? It's a meta struct. I am generating the struct at the compile time based on some descriptors we are providing. So we wouldn't get a normal member access here. So the only way I can provide users to read or write the struct fields would be the square bracket operator, at least as of today. And then the API returns either a struct field or an error. So it is wrapped inside a std expected, and then you can handle errors if you want. OK, so let's write our parser. But a fair warning. So template metaprogramming ahead. So I have had personally a love and hate relationship with template metaprogramming. Like whenever I start writing template type name ... I get faces from people. I mean, it's not an angry face, but it's not an happy face either. You know, it's somewhere in between. But I get the sentiment here. You know, like it's really hard to get it right. I mean, it slows your compile times. It's really, really obscure to read. You have to know a lot of recursion and functional programming. But TMP has its own place, right? It has places like here. Like you have to definitely generate something at your compile time. So let's explore like as much as possible. A little primer material. So it is not mandatory to know the complete template metaprogramming concepts to understand the talk, but it is still like I would say in the intermediary level. It's already in the intermediary level. But if you're interested to know and go back to basics about template metaprogramming, then I would recommend 2 talks. One is about variadic templates, CTAD and NTTP by Miro, and Miro's here. And then there is a talk by Bartosz Milewski about compile time functional programming. So these both would help us a lot. And there is also a few other. Maybe Chris Jusiak's talks are also good enough to lead, but it's more like his talks are more like implementation, like of some project. So what are we building? We can't implement every possible use case which we promised in the first the start of the talk, but we'll pick the 2 easiest possible use cases. One is a trivial struct. You have two integer members, for example, or you have a length fixed string / vector, maybe. So let's go ground up. So the first thing we would like to have is a way to represent your field, a single field, right? So to represent a field, we would have the name, right? And we would have the type of the field itself, and we would need a size hint, like what is the size of the field we would like to read. But as most of you might know, it's not possible for a very long time to have a string as a template parameter. It was never possible until, I believe, C++ 20, and then it was possible to have non-type template parameters. So you could now have structural types as your template parameters in addition to integral types. And then I found this hack about fixed string everywhere online, which is like a wrapper around std array. So you have an array with a std array of characters whose size is n+1. Why n+1? We need the null terminator. And then we have a constructor which takes a compile time array and then copies it into the std array. Some regular rudimentary members, like similar to your std array, like it's wrapping, in fact, it's wrapping the std array. And one additional small member I wrote is to string view, because then we can convert our fixed string into a string view. And to avoid user to pass in every time the size of the string as a template parameter, we have a ctat, compile time. Okay, the C++ has too many acronyms. I lose track of all the acronyms, but it is a ctat. And then this way we can avoid always passing in the size parameter as a template parameter, right? And then we say, okay, if I always pass in an array of size n, then always return a fixed string of n-1. And then there is a comparator operator, because we need to make sure that the fixed strings are unique in our use case. With that should be possible. You have a struct sample which takes a fixed string as your template argument, and then So now let's denote sizes. I mean, sizes are, we don't have to do a lot of gymnastics here. It's much easier. So I have size don't care. Maybe, for example, for struct fields, you don't need to say, if you have a nested struct, you don't have to every time say what is the size of the struct, right? I can compute for the user. So it's just like a placeholder, and it's private to the library. It's not exposed to the user. And then we have a general field size type, which just takes any type as a template parameter. It can either take a fixed or a len from field. And then the fixed size can be like taking a stitch size, the stitch size t as a template parameter. So that would be like exact counts. You know the size of the type you're going to parse at compile time, or you might derive it like from an existing field. In this type, you can then pass in the field name as a hint for the parser. And the field accessor is coming up later. Like I have tried my best to keep the talk linear, like going ground up, but sometimes, you'll have to jump the references, unfortunately. So now we can denote the name, the size, the type. So now we can write a field struct, and it takes 3 template parameters, the ID, the type, and the size type, and then we store them in as types inside them. And then I have the field value itself. Therefore, now it's possible to write something like this. Okay, now let's ramp up. We have our individual fields to be written, but how do we then have multiple fields? We'll have to have a complete descriptor of the struct. So now we have to have a type for the struct itself. So a small utility which we can write is a type list, right? We have vectors and lists which can hold values at runtime, but we don't have, at least from the library or from the language, a way to have a list of types at the compile time. So one way is to use a variadic template, an empty struct to which you pass in all the types you want to store in the list as a variadic, template arguments. So we need to have a literal, which we saw in the promise page. The literals for accessing our fields with this literals from the struct field, right? So we need to write some contraption to do that. And I write a field accessor, which takes a fixed string as a template parameter, and it stores in itself. And then a small namespace for the literals, and then I have a literal which can, when you pass in a string literal with the _f, returns the field accessor. But why do we need this? Because in the future we might have to apply constraints, right? We have to say, okay, in my struct field, I should only access fields which are actually part of the struct field. And that would become much more evident in the next upcoming slide. So how the struct itself is working. So again, we have a variadic template, and then two concept constraints. One is to ensure that all the fields are unique in your struct, right? It is just like your any other struct, even not our struct. Even C++ struct, you have to make sure members are unique. And then all the size dependencies are resolved at compile time. And what I mean by size dependencies are resolved is like if you put the fields from left to right and you start parsing from left to right, you have to ensure for a given field, the size which you depend on is occurring strictly to your left, right? So which means I have to make sure, go through each of them and then see if any of this field has a dependency. Yeah, it has one, and then go to the left and check if it comes to the left of it. Else I have to make sure, okay, this constraint is violated and you can't use the struct anymore. And then I take each of those fields and I inherit them into our struct field, right? So coming to the square bracket operator to have our fields accessed. So we have a square bracket operator. Again, I know a lot of templates, but then we take a field accessor as our first template parameter, and then I have a default second parameter, which is the field we are trying to look up for, and then I write a small meta functions. So basically, meta functions are functions which are executed at compile time. So you can either pass in like a type or a value to this meta function at compile time, and then you can get out a value or a type at the compile time. So in this case, the field lookup is a meta function which we are writing, and then it takes the type list of all the fields possible, and then it looks up, like it's like a std find if you can imagine, and then it looks up for our particular field ID in it. And if the meta function returns a field lookup failed, in that case, our field is not present in our struct which you're trying to access for, and then this wouldn't simply compile. You would get a fairly clean compile time error, and then else we would go ahead compiling the square bracket operator. So what we do is we know which field we were looking up for. Like we look up by name and then get the type of it, and then we static cast the complete struct field to the particular struct alone. And this, it works because we don't have any virtuals, right? And then we can simply object slice off all the other fields which don't we have, right? And then we return the value contained inside that field alone. Similarly, you can have a const version of it. Whatever we had is a non-const version, and then you have also a const version for it. But then how uniqueness and dependencies are guaranteed? I said I do this, but unfortunately, I have to do some hand waving here because it would take its own talk for that to explain how I'm doing that. So basically, they are the meta functions, right? And then they would have to check if there are no repetitions in the field names. You can take a type list and write a small recursive function which checks, okay, recursively if there are any duplicates in it. Or you can, in the actual implementation, in the current GitHub, it is like I have written a static set at the compile time, a container at the compile time, and then it checks if there are duplicates in it. And then also the other constraint I was talking about, the dependencies, the size dependencies. But we can at least look into how the lookup works. So I have a sentinel, like a field lookup failed. It is returned in this type is returned in case your lookup is not possible anymore, like your field is not there. I forward declare the field lookup function, and the first. So now we are in the world of in the compile time functions, right? We'll have to somehow leverage the template specializations to write meta functions in this case. So the first specialization would be the base case for our recursion. So if you have given a type list and the type list is empty, but you're still trying to look something for it inside it, then we have exhausted the list, so you didn't find your type. So in that case, I have a type inside the struct which is assigned to field lookup, like using alias. Or you have a field list, and then the first field which you're looking up is matching the ID which we are looking for. And then we say, okay, we then retrieve that field, and then we set that to the type alias. And the last specialization would be, okay, you still have some elements left, but the first head is not matching the ID we are looking for. In that case, we recurse for the remaining the tail, the rest. In this case, I have named it as rest. And finally, we have a field. This is the actual meta function, the field lookup underscore v, which would invoke the field lookup type and then retrieve the type which we stored inside it. And how, just to visualize how the accessor works, so we were doing the static cast, right? If you think of it, we have field A until D, and then the struct inherits all the fields. There are no virtuals. And then if someone says, I'm accessing field D, then it would just slice off the object and return you the field D and the value inside it. But in case if you try to do for E, in that case, E is not there in the struct field, so you would get an error something like this, right? It's not like super good, but this is the max we can get, right? As of now, as of C++23, that's the best we can hope for. I think Clang does a really good work for this, from what I've seen. So now we can also describe the struct itself. Like we have a way to describe our structure so far. So going forward, how do we generate the parser itself? So now we are going to. So far it has been the description part, but now let's slowly ease into the generation of the parser. So we might have to calculate the addresses from where somehow we'll have to reinterpret cast all the objects we are trying to read from. And for that, I have a list of overloads, one for, let's say, for the trivial objects, and for string, we might have one, and then other overloads, maybe for arrays, maybe for C-style arrays and whatnot. And then to calculate the size, again, we have a meta function. In this case, I call it as deduce field size. And then the deduce field size have three specializations. The first one is for any fixed size type, right? You don't have to worry about any runtime size in this case. So I just return if this template is instantiated with this particular field, and then I say and the structure is invoked with any of the, let's say if I pass in a struct field inside it, and then I just return n. For the vectors and string, it's the similar thing, right? But the only difference is for the vector, we will have to, if the length is from another field, now we can access the particular field with the square bracket operator, and then multiply the size of the type so that we can get the number of bytes we'll have to read for the vector. For a regular string, it's just 1. So you can just access the field, the length from the field which occurs to the left. So you will have to handle error at one point. So in this case, I have an enum called error reason. For now, we'll just focus on buffer exhaustion. We don't have to worry about other errors, but you might have something like validation errors, or you will have, maybe you're not able to deduce a type or whatnot. Then I have a cast error, which contains a readable error, the failure reason, and then we also say at which field we failed to read. Because you might have to say, you can't just say, yeah, my buffer exhausted. You might have to say, okay, it was failing when I was trying to read field X. And to read one single field, I have a small std expected called std expected of void and cast error, and it is called read result. I wrote a small monadic pipeline which kind of takes a read result and a callable, and this callable should again read it again takes okay, so in this case what it does, I mean, yeah, when I it's like really oh, okay. So a callable always takes it also always reads, it takes a stream and then it returns, I mean, it just reads the current field and returns again a read result, right? So you can visualize the pipeline as multiple nodes, and then each node reads a like a field, and then they return a box again. So then the pipeline in each node takes the box, looks into it, and then if there is no error, then it calls the next possible callable. Else, it just short circuits it. It just doesn't call the next one. It keeps just returning the error. And then we read at last. I have the struct cast impl. So again, I specialize it with all the fields because I need this, because I have to again have access to all the fields here. So that's why I have a specialization here. Just to keep readable, I have the actual struct field list and the result I'm trying to return. In this case, the API returns an std expected, which has either the struct or the cast error. And then I have a callable, like a call operator for our struct cast impl, and then it takes a stream as an input argument. I first define an empty field list, and then a pipeline, like a pipeline seed to kick off the pipeline, right? We might have to initially say that the pipeline should start. So I assume there are no errors at the beginning, and then I pass in the seed to the pipeline. So we have a fold expression which we expand, and then we know that we would read the fields in the same order because we are just expanding the template, and then this would be from left to right. It's like the associativity is maintained. And when we have a small callable, and in the callable we have a small magic to read the fields. And at the end, if the result has no errors, okay, then I create a result with the field list, or I return the actual error from the result. So what is this, the magic we saw in the previous slide? So I have to first take the underlying type from the field, because the field has 3 template parameters. So we need the underlying field. And then I check if the field is like is it like a struct, right? I have a concept to check that, and then if I see if it is like a struct, then I have to do this recursively. I just go on recursively, and then the errors are bubbled up from the recursive calls until the and like the highest possible. I mean, from bubble up until the stack, like the call stack. And if I find an error, I return the error from there. If it is not a struct-like, then I check if it is like either a constant-sized or a variable-sized buffer. Again, I have some concepts for that. If yes, I deduce the size for them with the meta function we wrote earlier, but now it's executed in the runtime. And then only if it is a variable-sized field, I resize the field. And then I do a simple read. I just do a read from the stream, and then I use the byte address utility we wrote earlier with the read size. If it fails, then I say, okay, we exhausted the buffer, and then create a small cast error object, and I return it. So the user-facing API is quite simple. We say, okay, you take a input stream-like object and then return a std expected of the field list or a cast error. But the field descriptors which we wrote earlier are kind of error prone. People might get things wrong there. So what I did is I wrote some like user-facing meta APIs, like if you think of it. And then, for example, a basic field is an integral field which you read from the stream, and then maybe the user wants to read like 4 bytes into maybe a 2-byte variable. So I have some concepts to check for that to avoid such errors from the user. And I don't want, for example, the user to every time manually calculate the array size, which they want, the array size in bytes, which they have to read. So I have also some utility user-facing meta APIs, and these would be much cleaner to be used. So now we have the field descriptors, we have the data layout, we have the class API, we have the actual implementation. So now the promise is fulfilled. So you can now write this code, and the link to this, the link to Godbolt in this slide is actually for the minimized version, not for the complete one which is in the GitHub. But there you have it. So how about benchmarks? Again, I have to do some hand waving here, but I think I have a good reason here, because I can't compare it with a manually handwritten parser for sure, because it would anyways be surely for slow. And I can't again compare it with Kaitai, because Kaitai, the generation is done outside the compilation time. It's already generated before the compilation is done, so it would be unfair again to compare it. I can't compare it with, say, other programming languages, which would again mean comparing apples to oranges. But I would try to bring some numbers in the future. Okay, but we are not quite done yet. What is the surprise we were talking about at the first? So the surprise is reflection. So C++26 would provide you reflection, right? And we have static reflection. In this case, you are able to introspect your program, and then you can reason something about your types and all your complete program. And then I also heard from Sebastian Theophil that we also have annotations for reflection, which means you could write something like that. So nowadays it's a trend to bring Rust in every possible C++ talk. So that's a library called binrw in Rust, where you can read. It's doing the same as our little project. So you can do all the tasks which we did now in this little library in Rust. But how does it work? So Rust has something called proc macros. So in proc macros, basically take the complete program, and then if it sees a proc macro, the compiler would parse and then take the AST and then inject the tokens into your proc macro functions, which is also written in Rust. So you can then manipulate the AST and then inject the tokens back into the compiler. So with that, they can write attributes, which they call attributes in the Rust world, to do this. Unfortunately, C++26 would have a reflection and also the annotations, but the problem is it doesn't have a way to generate code, not yet. That's not yet supported. But what we can still do, we can use our good old friend template metaprogramming to generate the code, but just have the user API with the annotations. In this case, you can just simply keep the underlying library as it is, and the user-facing APIs would just change for the types alone. Only the types would change. Like, user do not have to care about going everywhere and to change the struct cast API. So in fact, the code which we wrote is kind of compatible with the C++26 reflection. So the code actually hosted in GitHub is at least striving to be that way. So now you can do something like that. I mean, not now, as when we get reflection, we would be able to do that. And it looks cleaner, much cleaner. We are partially breaking the code, because the user will have to go back and change the struct now, but it's for the greater good. It's much more readable than our template metaprogramming version. The best part is you would then get regular member access, because you can generate structs, and then we are not in the meta struct world. We are now in the normal struct world. So then you can have lens, but the API can be backward compatible. So that's about it, and that's my little project. So that's the link to the Godbolt and also to the project, and so far the Godbolt has not timed out, so that's fine, which means it's not that slow as of now. So don't be afraid to do projects, even if it becomes outdated in the future. Even if you fail, it's okay. It's fun. You can crash compilers. I have crashed my compiler a lot. I have crashed my text editors because clangd didn't support certain features. And then I had to write a Python script to, like, with some like fancy graph algorithms to generate a single header, for example. So it's fun. Like, don't be afraid to do projects. And it takes a village to keep a project working. So yeah, I would be happy to collaborate. And then, yeah, if you're interested, please let me know. Yeah.
Hey, thank you for the talk. Can you go back to the slide with C++ 26 reflection?
Yeah.
It's more like just a question if you tried or not before. Go back when you said C++ 26. Yes. There is a library called boost.pfr, which allow you to do introspection with C++ 20, where you can get size of the structure. You can access each field by index, and you can get the name of the field. If you have tried that library, have you played around? I'm just curious of your experience.
Yeah, will do.
Okay.
Further questions?
Okay, then. Thank you.
Thank you very much.